Welcome to Clean Titans. Today we're exploring the intersection of electronics, AI, and the clean energy transition with Kevin Cameron, an analog mixed signal expert at Present Energy. Kevin, welcome to the show. Please introduce yourself and tell us a little about your background.
Thanks, Ali. I'm Kevin Cameron. I live in Silicon Valley. I grew up in Scotland, went to university there, and studied electronics. So back when I was doing it, it was much more analog electronics for most people, and so I did a lot of that, and then discovered that it was probably better to actually be a software engineer. Migrated into software engineering, but in EDA, which is like tools for chip design. So I was not moving that far intellectually from the electronics when I went into software. And I sort of studied how to do some simulation stuff mostly there. And then there's parallel processing I got into because of that. That actually got me the job here in the USA back in the early 90s, working with VHDL simulators, and that's what brought me to Silicon Valley. So in Silicon Valley, I've been dotting around doing software for simulators and then using the simulators in verification. So I'd say over the last couple of decades, a lot of the work I've done is just digital chip verification. And maybe 15 years ago or a bit more, I decided I would try and do startup stuff, which is how we got into doing Prezent Energy and some other startup idea things which are running in the background.
We're thrilled to have you. Present Energy is focused on accelerating the energy transition through advanced technology. Could you give us an overview of Present Energy and your role there?
Yeah, so Present Energy is actually a sort of couple of pivots away from where we started doing startups. So initially, I was looking at doing EDA-based startups, and the people I was trying to team up with weren't very keen on software and EDA and wanted to do something in clean tech. And recently, at the time, bought a solar system. It cost $20,000 or something, and it didn't work when the grid went out. So I was thinking, it's like everybody's going to have electric vehicles in the future, and that'll be my next one. How do I use my electric vehicle's battery to keep my house running was kind of the idea. And so we started there. And then it was during the recession at the time. So we were trying to launch and didn't get a lot of traction. So we sort of pivoted a wee bit into, can we make solar easier to install? And then it all sort of went on a back burner for a while. And then more recently, I was looking at something in EV charging, and it kind of looked like our original problems were just trying to get people to use more solar and the EVs as storage. And then we were looking at, well, we really need people to be using EVs as much as possible. And there seems to be some blocks to that from the infrastructure charging point of view. So we were looking at how do we fix the EV charging infrastructure problem for people. And from a startup perspective, some of this is interesting because the fossil fuel business is $1 trillion a year US. So if you're a startup, you only talk to startups that have a large TAM. So the addressable market for this is displacing fossil fuels, and that's an awful lot of money. And although some VCs don't like you saying that you only want a small slice of a big thing, this is a big thing. So that's part of the reason for doing it.
You have extensive experience in analog design, particularly in power electronics. How does your background in power electronics relate to the work you're doing at Present Energy?
Yeah, so back originally before it was Prezent Energy, it was a thing called HEMBUS. And what we're looking at with HEMBUS is like to get better interaction between the pieces in sort of clean energy. So solar systems, there's very few standards for what the voltages and things are. So we're looking at it as like, can we standardize on various voltage so things just plug and play? So the idea with HEMBUS was a DC power bus, where the grid is like very solid low impedance thing. So it drives even 10 volts very solidly. What we were looking at is a high impedance DC bus where the voltage floats up and down depending on how much energy you've got. So you can do things where as the solar is adding more power, as the sun comes up, the voltage will float up and you can say, okay, I've got enough energy now. I can heat water, or I can do something else. You can switch things on because I've got the energy to do it. So that was the idea with the HEM bus. And we would run that around your home. The idea was to do it differently from others. So if you go to and look at people working in this space, they tend to go through the breaker panel. So you can look at like startups like Span.io, Coleman Systems. They work through the breaker panel, but the breaker panel is like expensive to play with. So we were looking at working at wall sockets instead. So the idea was that we would have this DC power bus running around your house, and it would go to the things that were interested in DC power and also wall sockets for failover. So basically, we're taking the pieces that you would get in a UPS and saying, okay, we can disaggregate the UPS. And we normally inside something like a UPS or an inverter, there's a DC power bus. So we were just saying, okay, pull out that DC power bus and run your home. And like 200 volts is about the level you need for doing sort of 110 AC stuff. That was the idea there, is if we make the stuff kind of modular and standardized, then the pieces are cheap. So rather than like big expensive inverter, you have half a dozen small wall socket things. So we recently applied for a patent which eliminates the big inverter entirely. So the original scheme I had a big inverter for the solar, and then small inverters for driving things from the DC, like your fridge or your microwave or whatever things you want to drive around your house. But that was like as much stuff as we needed, really. We only needed one inverter, or really what we needed was like multiple inverters that work together. So the current scheme for HEMBus is that we have a bunch of wall sockets around your home, which each has an inverter, so it can drive the appliances that are attached. And if it's not doing that, it can drive the power from the DC solar stuff into the grid for you. And the idea, again, is that those inverters should work both on-grid and off-grid. So if somebody throws the breaker on your house, then those inverters just keep working, driving the stuff in your house. And you can fiddle with where the switches are to disconnect bits of sub-circuits and things if you need to. But that's kind of where we are now. And the original idea, again, was smart wall sockets. But that was like years ago. Now you could have very smart wall sockets. We're looking at doing very
Super
smart.
smart.
Yeah, we're looking at like and do things, and I work with people at the Open Compute Project on this kind of stuff, where we're trying to do distributed computing, so we can distribute the computing into the walls in your home in these wall sockets, and that's useful if you're trying to do things like AR, VR systems, where that stuff's going to be millimeter wave radio. So what we're looking at with the DC power scheme when we originally did it was we put fiber in the DC cables. So we get extra value in wiring your home for the DC power by putting fiber in for communication. So that's all still a good idea, I think. But it didn't sell at the time, and we still haven't built the components because a lot of stuff's quite difficult. Because if you build something people interact with, it has to go through UL certification, and that kind of creates a hurdle for getting into the market. So you need funded to do anything. At the moment, we're pivoted in Present Energy as like the electric vehicle piece rather than the solar piece. So we're looking at sort of deploying as much EV charging as we can in the environment where the EVs are, so we can see where the EVs are, and then we can add solar. So the solar is now sort of secondary charging EVs, but the ultimate goal for Present Energy is we collect as much solar energy as we can during the day and feed it into your home at night. So we're sort of just solving the charging problem, and then we're going to go back to where we started and solve the energy management in your home problem.
They just started doing V2G in Australia. Have you
Mhm.
looked at some of the companies involved in that?
There's a lot of people doing that. What we have is we were trying to do the robot thing with a transformer coupling. So this goes back to my roots in power electronics. When I started, they were actually just switching from bipolar over to power MOSFET devices. And the thing there is like the bipolar stuff works at sort of audio frequencies like 20 kilohertz for the transformers. And those transformers you can do where they couple magnetically. So you're getting energy into the core of the transformer and then sucking it back out in the secondary winding. Once you go over sort of 100 kilohertz, then the transformers work differently. You can't actually ramp the field in the cores very fast. So what you're doing is just going winding to winding. So normally you want to wind your secondary around your primary or vice versa, to get the coupling you need for that transformer to work. What I was looking at was like you do that thing where you've got cylindrical pieces. You can actually do them conical or you can do them flat. It's all a transformer. So a lot of the wireless charging you see is two flat windings that are talking to each other. What we were looking at doing is a conical thing. So there's a cone, which is primary, and it's got a winding on it. And then there's a receiver, which has got the winding inside. So when you push those things together, the primary and secondary are lining up, and it's a high efficiency connection for the robot. So that's the base IP that we're dealing with for getting the robot to connect.
So, what are the key challenges in designing power electronics for renewable energy applications?
One of my threads is like to get the tools for this into the environment for people to use so it doesn't cost them anything. So I worked on the Verilog EMS standard. Comes from when I worked at Rayco Redac, my first EDA job in the UK, we were looking at, well, do we need to make signal stuff work? I can't remember why the government was asking for this, but we had to do a report for a government thing, and I did a short report for that. That kind of got me interested in the space. And then when I worked at Chronologic on their digital simulator, they kicked off this Verilog AMS standard thing at Accelera, and I got involved in that. And this is one of my claims to fame is the Connect module, which gets you from analog to digital views of things in the simulator. So the Connect module is a sort of artifact of simulation which converts from one view to another. So that's the intent there, was that we would have a standard language for doing circuit design that covered both analog and digital. I would say that now we're not much further on than we were in 2000, because although the standard came out, it missed a couple of pieces. There was one piece that was definitely wrong, and then there was another piece that was definitely missing. So there was where the Connect modules got placed was wrong, and the back annotation wasn't there. So really what you want to do is you take a spice level kind of thing and replace it with a behavioral model that works the same way but goes a lot faster. And then you're doing back annotation with SPEF, which is analog wiring in between those behavioral models. And that would let you do a very fast simulation of things like power electronics. But what's happened is that because it belonged to Cadence and they pushed it a particular way, it never really got adopted. So that's changed in the last year or two. There's a thing called OpenVAF, which is like integrated with at least NG Spice, which is a Verilog A simulator. So we now have the open source capability to do this stuff, but it's still not all plumbed together. So I'm kind of working in the space of like, we get open source tools that will help us design things. And also at this point, can we do the tools in a way where the AIs can use them to design things for us? So if you look at something like Fold as an AI, what it's doing is like how the chemistry works and at the atomic level to see how things fit together. And if you've got simulators that work fast enough, the AIs can learn how to design things at that level. So my goal in life is to give people the tools to design these things for free and also enable the AIs to do it for you. That appeared to be a bit of an uphill struggle.
That was my next question. You're applying AI to EDA,
Yeah,
electronic
yeah.
design automation. How is AI transforming the design and simulation of electronic circuits for clean energy technologies?
It hasn't really yet, but it's one of these things where I didn't start out there. It was like a few years ago. There was a guy who's at Stanford, Professor Bernard Woodrow, and he actually started in AI before I was born by about a year. And what he did was he developed this stuff called least mean squares adaptive filtering, which is used in a lot of electronics for communication. But then he sort of developed that into control theory thing, where one of your problems with complex control systems is you don't have visibility into the thing you're trying to control. So the only thing you can do is like bat it and see what happens. So there's a digital twinning technique where you say, okay, I'm going to observe what the thing does, and then I'm going to twin it into a neural network. But the neural network's just a mathematical thing in matrix math. And what you're doing is what they call gradient descent optimization, where you're looking at the difference between your model and the real thing, or an accurate model. So I was looking at it and saying, okay, real thing could really actually just be a spice model of something which is accurate. And what I want to do is create a fast behavioral model. In electronics, the spice simulators are trying to apply Kirchhoff's current laws usually. And that means that there's a lot of connections between the ground and the DC power supply in electronics. And the simulator is trying to work out what's going on this way. We're actually interested in the behavior going that way on the circuit. Usually, was its input, what was the output, and what's that relationship? Once things powered up, we're not really that interested in how this bit sort of interacts with that bit, except very loosely what its power draw is. So you can convert like spice level circuit into a behavioral model which has similar accuracy and about the right power thing, but just goes a lot faster. And what I'm seeing now is that all these AI accelerator chips that people are making are probably quite good for simulation engines in that space. So it's one of those things where, for me, there's a bit of a convergence between all this analog mixed signal stuff and neural networks. Neural network, particularly a spiking neural network, looks a lot like a circuit. So there's a sort of convergence on that level of technology for compute and
Can you provide specific examples of how AI is improving the efficiency and performance of these circuits?
it hasn't really hit yet. I know how to do it, but nobody's paying me to do it. So I haven't got the opportunity to develop stuff like that. So the model building I do is sort of partially automated. And then I'm still working on trying to give the simulation the hooks to do this stuff. So one of the things there is the AI piece is a digital twinning. So we're looking at, like, with all AI, an LLM is trying to digitally twin aggregate human behavior. So you're just trying to get one thing to look like another. So at the Open Compute project, what we're looking at is we've got a software workload, goes reasonably fast, but what we'd like to do is have it run faster and be more efficient. So what we want to do is digitally twin the software behavior into better hardware. And that's where it's useful to have things like the thermal simulators and the power simulations and stuff to go with the hardware's running. So you have a high level models, performance models of things like an ARM processor x86 when they're running particular code, and see how that can be optimized. So most of the processors work really well if they can stay inside a small amount of memory. If you give them a large amount of memory, then you're spending a lot of time and energy moving things in and out of DRAM. So see things like HBM designs, moving data in and out of that is not particularly efficient. Digital twinning of a sort of model of how that works, you can fiddle with the digital twin and see what happens when you sort of rearrange the code and make it work differently. So I can see where I want to use it. I did a presentation for the Chiplet Summit on using AI and digital twinning techniques to improve how the software ran, but nobody's built it yet. But in the last 5-6 years, I've seen a lot of people develop special processors. One of the things we're trying to do at Open Compute Project is develop a simulation environment where you can try mapping your software load onto a bunch of specialist processors, and you get some idea of what the behavior is going to be like. So there's a whole lot of accelerators people would like you to use, but there isn't really a good methodology for getting them in. I'm motivated to make that work because I want to use that platform for doing circuit simulation. The other guys are all trying to do things against, they're competing with NVIDIA. My view is, like, I like your hardware, but I don't want to compete with NVIDIA. I just want to build a better simulator. Then I can go build better chips. So it's all the pieces are there. It's just like they're not brought together yet.
Hopefully, you'll do it at some point.
Somebody should.
Parallel processing mixed signal simulation is one of your specialties.
Hmm.
How does this technology contribute to the development of advanced electronic systems for the smart grid and EVs?
So the smart grid is another one of these things which is large and complex, where you want to digitally twin it. So if you take the grid as is and say, okay, I need a model of the grid so I can work out where to put my solar panels, where to put my storage, things like that. So some of these problems are really the same problem. So me trying to accelerate code in a compute farm is pretty much the same job as trying to optimize the power grid at some level. I'm trying to sort of get something in the power grid and say, okay, I want to digitally twin that into some neural networky. And once I've got a digital twin of the power grid, I can play with that. So in a Linux, you can say, okay, I want to take a piece of my simulation, clone it, run an experiment, see what the result is, and then I can decide where you want to charge an EV or put in a solar panel, or maybe I want to tell somebody to park their EV somewhere particular. That's where the AI sort of tools come in. It doesn't really matter at some level what thing you're trying to digitally twin. A lot of the techniques are the same kind of gradient descent stuff. Mostly what you're doing with the AI generative stuff is you're saying, okay, generative AI is going to give me a starting point. It's going to create a circuit or something like that, but it won't be the right circuit. You can get them to create code for you. You run it, it'll fail. You talk to the AI and say, well, that didn't work. Can you fix this line of code? And the AI will say, oh, yeah, well, I'll fix that for you. So we're trying to get to the point where we can do that for circuit design, where the generative AI will give you ask for a PLL and it'll give you a PLL circuit. And then you say, well, I'll try and make it work for this particular frequency things, and like the reset, you're going to go back and forth, but the AI will have a fair idea of what to go at in the circuit and add PCs, and the simulation is what tells you it's actually working or not. If the AI can get you close with the generative piece, the gradient descent piece will get you the rest of the way. And then, what the AI can't do for you, you have to do yourself. But hopefully that gets to be a smaller and smaller piece as you go along. I've seen a lot of analog circuits where a lot of the stuff is boilerplate, just switching things off and on, reference currents, things like that. You can get the AIs to build that stuff for you fairly easily, or just automate it. It's not even AI work, a lot of it.
What are the computational challenges in simulating complex mixed signal systems, and how do you overcome them?
For the big circuits, if you try and do an all analog approach like spice simulation, there's this thing with matrix math where it gets exponentially harder. The problem you see is the people who do the matrix math solvers for spice simulators don't really understand the circuits. So they don't know where the compromises are that they can make to get better results faster. So they're usually mathematicians. So you've got mathematicians who don't understand the circuits, building these simulators where they're super accurate, but then you can't actually build things accurately. So the accuracy of a spice simulator is way beyond your ability to build anything. Um, so basically, you're looking for these trade-offs where you can say, okay, you can sort of break this down into pieces where we use event-driven communication between pieces rather than trying to get them into the matrix and solving them. So a lot of stuff is sort of unidirectional and then multi-domain. So one of the things if you're doing RF stuff is to deal with it in spectral analysis. So you can take the spice level model and create a spectral model from it, and the spectral model is just dealing with frequency changes. So basically, when you're doing something like a cellular phone, the baseband is working out what it wants the spectrum to be, and then there'll be a D2A that injects that into the analog circuit, and then you've got the analog circuit creating the RF signal for you. Rather than do the D2A in simulation, you can just say, okay, this is the spectrum. I'll just like it as a spectrum, and then everything is stable unless you make a change at the baseband. So rather than trying to do a spice simulation at like gigahertz or whatever, you're just dealing with baseband changes and propagating them through the spectral filters. This is where I did propose some stuff for the extensions to system Verilog to handle this. But what you see these days is like don't want to change the simulators they have. So it's very hard to get anything through like IEEE committees that are changing hardware description languages. Everybody's got their tools. They don't want to change them. They might want to tweak a little bit, but there's no major stuff going on there, which is why I'm at these days I'm proposing federated simulation as a solution for the bigger problems. So basically you divide up your system into some regions which have their own simulators. So with the RF stuff, you have baseband processor type simulators, which are going into analog behavioral simulators, which go into RF spectral. And so one of the things there is that for something like RF stuff, particularly, there's a fairly high latency between you sending something on an antenna and it actually getting somewhere. And you can take advantage of that in simulation and collapse the time. So as soon as I know what something is, I can give it to the other pieces of the simulation. But rather than it being miles away like it would be in reality, it's just the next processor. So you can accelerate how things work by getting all the simulation in one box where it would actually be distributed. And that helps with things like when you look at the power grid is a very slow beast. So you can definitely simulate the power grid in real time using spectral model approaches. It's just 60 hertz at 110 and changing. It's fixed at that until something bad happens. So you're doing event-driven stuff in spectral space, and the models for that come from digitally twinning the analog behavior, either by getting the circuits from somewhere or just observing it.
You've contributed to the development of Verilog EMS and system Verilog standards. How do these standards facilitate the design and verification of complex electronic systems?
It's one of these things where you want to move into open source. You need points where you can substitute the open source tools. And the standards are very important for letting you sort of take an open source thing and plug it in where you had something commercial previously. So it's one of these things where you kind of want to sort of break a lot of the design stuff away from the big EDA companies. You don't want to do things in a way where it's proprietary and you can't shift it. And that's where the standards come in for me. Is like the problem is that a lot of the people who work in open source, their view is that they're just going to do a cheap version of something they don't want to pay money for. So my view is like open source should really be the better version, and we can get there if we've got the right mindset. The stuff in EDA that okay, you need to support those old flows for a while, but really what the goal should be is to do better. And I think the AI will let us do that. But if you're building AI on top of proprietary tools, it's not going to go that well. So the thing here is to try and sort of do better with the open source tools and give them to everybody. And the sort of ultimate goal there is to enable better hardware design. So the free simulation tools and the open source stuff are going to enable us to do a better job on the design.
How are these standards evolving to meet the demands of emerging clean energy technology?
You don't see too many standard efforts in that space. It's just that I'm not in that space so much. There are people who are working in things like, say, ADR, which is smart grid protocols for energy management. So that popped up because somebody wanted to know how to manage power in their compute farm. So there's sort of overlaps between these different areas. So it's like demands for a data center that now has to talk to its energy supplier and see, well, is the sun shining? Can I go fast? A lot of these things interacting, but it's across domains, and humans are not particularly good cross domain. This is where the AI comes in. The AI can understand all domains and can say, okay, probably don't want to run this job until the sun's up. It's important. Maybe I'll burn some gas to do it instead and fire up a generator. The complexity is just too high for humans. So human systems are just horribly inefficient a lot of the time, just because the way we have to divide and conquer because humans are limited. The AIs are obviously less limited in certain dimensions at the moment, and that creates opportunities for optimization. So I'm mostly trying to give the AIs the tools to work with. At the moment in EDA, the tools are not particularly good for humans, and that means they're not good for the AIs either.
Present Energy is looking at the world at the end of the energy transition. What are the key technological challenges that need to be addressed to reach that end state?
Yeah, I think it was Tony Saba said that we could transition from gasoline to EVs in a decade. So the question is like, okay, if we're doing that, what does it look like?
Norway has shown that in 6 years they went from 20% to 80%.
Yeah, I think they're burning oil money to do that.
Right.
But it can be done. So the question is, what's stopping it happening? And so you're seeing people in Silicon Valley, people buy their Teslas. They're mostly charging at home at night. That works fine for a whole lot of people. If you're trying to charge during the day, it's a bit harder. If you're at work, you talk to people who are, cars around, they have a little, where he says, I'm going to move my car. And then somebody goes with them and swaps their car in to get onto the fast chargers because there's only half a dozen fast chargers. So what we're doing at Present Energy is saying, okay, we can solve some of these sort of infrastructure problems by going to robotics, because the robotics stuff exists in the existing environment. Your robot can go find a plug in a wall somewhere to plug into and charge up, and then go find your car and discharge into the car. So the goal is to try and get as much energy into the cars as possible during the day so I can use it at night, V2G. But you start with that, you just need to get people to buy the EVs. So if we make it easy for them to use an EV, they will buy an EV over something else. So in theory, because electricity goes everywhere, you should never really have to think about charging your car. This should be easier than gasoline. I mean, it'll charge at home or discharge at home. You park. You're never far from electrical power in the US. So we're looking to leverage all that infrastructure that's there already and accelerate EV adoption. And one of the things there is where the smart grid piece comes in, is that the grid itself can't actually support that future world. It can fiddle with the transmission and go to DC on the power lines. You can use storage wherever you need it. You will be able to double the capacity of the grid. But the cars themselves are equivalent to what we're currently doing. So we're looking at like that, and heating and cooking are all going to go electric. So you're looking at least triple the demand, and then you look at all the demand for AI and stuff that's going on and say, okay, it's quadrupling over the next decade. And the only way to get that power, because you can't get it through the grid, is by going to distributed solar and wind. So what we're looking at is doing things like, you're charging your EV, we're going to throw solar in there to do it. We don't have to go through the grid for that. We can just put up solar carports that charge our robots. The robots charge the cars, and then you go home and you've got the energy at home now. So you don't have to pull the energy that you're using for cooking from the grid. You've got it in your car. So the car is now cheaper because it's subsidizing your habits. And that's kind of the goal here, is like EV should be cheaper. This whole thing is cheap. Solar free. The EVs are like low maintenance, and they're you can get paid for the energy storage they can do for you. So
They can actually make you money that way. I mean,
yes,
it's
yeah,
already cheaper, 88 times, 9 times
yeah.
charged with electricity rather than fill it up with gas.
And then sort of what we're doing is looking at the problem of people living in apartment complexes in the US. We're saying, okay, if you live in an apartment complex, maybe you could car at night, but you can charge it during the day and bring it home. So we're just sort of reversing the normal charging pattern. we can do stuff with Teslas that are coming onto the market that nobody wants. You can go fix those so they work with the robots and then sell it to you on a lease where we actually give you a big discount because we're using it as storage in the grid. So as long as your car is available to us to use it for grid storage, we're giving a discount on that vehicle. So we can get EVs to everybody doing that cheaper than people will be able to get gas vehicles. So really we can do an awful lot of acceleration in EV adoption and then fossil fuel displacement in theory.
Well, I really like your idea of robots coming around and charging cars. Then you don't have to have charging stations at every stall. Like in China, they're putting charging stations practically in everywhere. Every stall has a charging
Yeah.
station.
So this is trying to avoid that problem of like digging everything up. So the population live in apartment complexes. Most of those it's pretty impossible up and put EV chargers everywhere, and then nobody wants to get up at 2 a.m. and move their car onto the charger. So like we're looking at it as there, it may not be us that do the robotics, going to do robotics, and it's going to be hitting these like dwelling people.
You just have a couple of robots that charge cars all night or all day.
Yeah, which is
Right.
a bucket brigade. We're trying to do bucket brigade where the robots are small; they just go round and round. So cheap robots, lots of them. They fit in. They're small, so they fit under the vehicles,
Oh,
and then so we're not taking up extra space with our robots.
even better. What role do you see smart grid technologies playing in achieving a fully decarbonized energy system?
It's pretty essential. Basically, the energy of the future is solar. Price on solar just keeps dropping. There's Swanson's law kind of dictated that, and it's not like chips. So and you had Moore's law, which is a learning curve, and then it ran into problems because they were doing optical lithography. So it's like sort of hit 28 nanometer and then kind of flattened out in cost. You're not doing that with solar. Technology doesn't have that same limit. So it can just keep getting cheaper until it hits some lower fundamental limit. And basically, you should be able to at some point put solar on any.
Well,
And
the expert, new energy expert says that so cheap that it costs about the price of buying coffee once a day
yeah,
for a week. You can buy
mhm.
a panel down to like cents per
Yeah.
kilowatt in some markets.
Yeah, the problem has been it in. So in my house, we have our installation that was done by Solar City, for 20 years ago. But what we were looking at with the original Hembus thing was like, we can go modular with this. If you want 5 kilowatts of solar, we'll give you 5 1 kilowatt standard modules for your tank. One way of making it cheaper. I have my ideas for doing solar roof tiles. I'm sure other people have. At some point, somebody will fix that. And again, the power electronics comes into that, and using say AC coupling rather than DC coupling and things, because DC has like with corrosion and stuff like that. So in the last few years, you've seen a lot of advances in GaN and silicon carbide technology, where things can go a lot faster and be a lot more efficient. And just the price coming down all the time means that you can go for much more exotic approaches to doing the power electronics than you used to be able to do. Watched power electronics. I used to do it as a job for like 3 decades, and like little changed. And then the gallium nitride and silicon carbide stuff arrived, and the whole game changed, and like just a whole lot of stuff going on. And it's one of those things where this is where the tools help you. If you've got tools that understand what you're trying to do, you can design exotic things. I put out some stuff for the IEEE Pels group on YouTube. And we had somebody talking about doing the cable in a US as the inductor. So you got like they do a switch cap stage on one end, stage, and then another switch cap stage on the other end to get power down this USB cable. And I was kind of looking at it saying, well, the people I know who try and do this SPICE simulation just can't get it done because it doesn't go fast enough. And this is where the tools come in and say, okay, if you've got an idea like that, if the tools are open source, free, and smart enough, you can design these places. If you have a bright idea of where you want to put your power electronics, it should be easy to do that. And Zeiss is the open source tool that I'm looking at as a good for this kind of framework. And somebody did a whole free thermal simulator with Zeiss that's up on GitHub. You can take these various efforts and like put them together with federated simulation, where suddenly it becomes a lot easier to design these things, and we can accelerate how fast we get there.
EVs are a crucial part of energy transition. How is Present Energy developing technology to make EVs the obvious choice?
That goes back to making them easier to use. If you don't have to think about it, it works a lot better. There's the car thing of like, if the cars are equipped and the robots are working, you never have to think about charging, and you're actually getting paid for moving energy around the car. So it's just cheaper. Wouldn't you do it? It's
Right.
sort of
If
practically
you bring down the
paying.
cost, it's a no-brainer, right?
Yeah, and I'm looking at things like the smart grid thing. What you're looking at more like a micro, and so microgrids tend to go with VPP plans. So community level microgrids and VPPs go together. And if you do something like mash a VPP, which is a virtual power plant, with something like a credit union, you can say, okay, I need to buy a car, and the credit union will say, oh, well, if you sign up for this VPP plan and stuff, like, we can give you this car really cheap. And complex. See how the pieces would fit together. The harder things are things like trucking. So there's a whole thing with trucking across the US, and you think, okay, the infrastructure for charging trucks, if we go to megawatt chargers. And that's part of what we're looking with the robots and things, is saying, okay, if we've got multiple robots, we can swarm charge a big truck, because the batteries tend to be modular. So you can say, I'm going to do a charging interface per battery module, and the robots will run in and find that and charge them. Um, so there's that part of it, and then some that area is like, okay, the solar energy for that coming from, and you look at doing agrivoltaics for supplying the energy for batteries. Talked about doing things like robot battery, where it sort of drives somewhere to a solar farm, charges up, drives out to the freeway, boost charge a car wireless, and then zips off and recharge well. So can get power across these long bits of the US that have no real infrastructure at the moment.
Or you can put some tracker solars. Access trackers can increase the amount of solar produced 50 to 70%.
It
So you
doesn't
can put a
matter
bunch
so
of
much.
those.
Yeah, these days you can go vertical and flat with the solar, and it's cheaper. If you can make a flat surface like a roof, that way they'd have a lot of angled panels. The reason it's cheaper is because most of the cost is not the solar. The solar PV is the cheap piece. The expensive piece is like the framing, holding it up, and the inverters and connecting it to the grid. So it's a lot of what I'm doing is saying, well, we can throw away the grid connection. You can do that with computing. You can say, okay, you can build a data center where it just talks wirelessly. You can put that out in a lake, and floating solar, this thing where you can build a little rest that can put panels and have maybe batteries, and they talk to each other wirelessly, and they're sitting on water, so they're cool. So lots of things you can do with solar, and it just keeps getting cheaper.
Yeah, you can couple that with floating solar panels and floating
Mm.
batteries.
Yeah, there's lots of opportunity, and it's global. You just where it's sunny all the time. You just stuff in the middle of Africa or something. Quarters of the planet's surface is ocean. There's the question of how do you engineer for that. I've got friends who work in that kind of tech. It's not something I have any expertise in, but I can think of things I would like to do out there. So robotic boats with kites, and all sorts of interesting things you could play with.
What are the biggest hurdles to overcome in order to increase EV adoptions?
It's just that convenience. I think I'm connected with somebody whose job is the luxury cars and the luxury car experience. We can say that robots are like going to work. They can work in that market where people just want to pay for it and have a cool robot. And then we can work the technology down to working for everybody. But it's basically we're sort of dealing with the missing infrastructure by going to robotics. So if the infrastructure was there and you could just park everywhere and plug in, people would do it. And there wasn't much to charge your car. So I think the thing is that most people don't realize that cars that we have that you run on gas, are catering to people who go a long way by having large tanks, but that's only a small percentage of the people. Most people drive like 35 miles a day. The average trip something like 5 miles. So that's like 2 kilowatt hours of energy. So, I've got an EV, and it's rare that we actually empty it. Mostly drive to the shops, keep a little bit down, and it recharges in less than an hour.
In China, they're do the swapping within a few minutes. And
Mhm.
so for everyday use, they can give you a cheap battery and it costs you very little money. And then for those long distance trips,
Mhm.
they can give you a semi solid state battery that gives you enormous range, like 500, 600 kilometer
Yeah.
miles.
And
And
I
then
think
you
that,
can just
yeah.
use that for those times, pay a little bit
Mhm.
extra, and then
They're not hackable. The solar panel itself is not hackable. In the previous discussion, what was hackable was the inverter, because the inverter is like bad mode that it can operate in. So eliminating bad modes is one of the things. So you want stuff to just work, not have ways in which it can fail detrimentally. I mean, the thing that I've got is how to do defect analysis using AI to so we do. The idea is that if something can fail, you have a failure model as well as a good model for it. So if you've got something like an inverter, you can say, okay, I can analyze the inverter and work out what ways it can fail, and maybe there's 3 or 4 ways it can fail I care about out of thousands. So I build models for those things, and then I can simulate what happens with my smart grid simulator when things fail the way that they might possibly fail, and I can be smarter about it. So it's basically predictive. You can kind of something fails a particular way, I would see this behavior in the grid, so I can go look for that behavior, and then I can say, okay, if I see that behavior, I know something is likely to fail badly. So I can send out the maintenance crew now. So, and again, it's just optimization. Like you're saying, okay, what's the best time to actually replace this thing? Should I look for a particular sort of mode of operation before it like needs replaced? Or these kind of things.
How can industry and academia collaborate to drive innovation?
I think I would go back to the standards thing and say like we different kinds of standards bodies. So I mean, at the moment, in EDA, I've got IEEE and Accelera, and then there's a couple of oddball sort of bodies in Europe. The guys are not a proper standards organization as yet. There was an effort like years ago, I think, OpenStand, that were like trying to do this more formally for the open source community in Linux. But it's the standards where you basically you can plug and play with things, which give you the ability to accelerate change. If you can we can use the AI to do that. Maybe we can get the AI to look at something and say, tell what the nearest sort of standard way of doing this is. Be a standard from what you see and build from that. One of the things that Open Compute Project is currently, the internet's sort of a lot of intellectual baggage but for say IPv6 are quite good. So the question is, can we take steps of IPv6 and sort of detach them from the physical layer Ethernet for communication in general? So it goes into the IoT space of plug something into the network. I kind of just want to know it's there. So at the moment there's this thing where when you buy something, you have to tell it about your Wi-Fi and put in passwords and things like that. Change that so if you've got the standards for it, it just sort of automatically attaches itself to the networks and says, "Hey, I'm here." And then you'll pop up on your phone and say, well, so-and-so is trying to join your network. Are they allowed? And you just say yes. And then like your robot or whatever works for you. so those definitely standards efforts kind of things that we accelerate.
For aspiring electronic engineers and software developers interested in contributing to the clean energy transition, what advice would you give them?
Buy an EV and install a lot of solar. It has its own inertia at this point. We're trying to push it. There are bigger problems like the other issues which nobody's really addressing. The fact that solar is so cheap now means it's like pretty unstoppable. I mean, with Prezent Energy, that there are ways to deal with the EV charging problem. So I would say, sort of solve problems now. You just have to keep selling it, and we'll get there. But then, clean up the atmosphere. We're just not. We get to net zero at a reasonable speed, but at the same time, that's not fixing the problem. So the thing here is probably much more sort of do chemistry, work out how to pull all that carbon dioxide out of the air. Do AI, with stuff to work out how we actually fix some of these problems faster.
But I mean, young engineers and software developers who are just getting into the field, what advice would you
It's
give them?
to do physics and math. The rules of physics and math don't change. AIs are not particularly good at physics and math yet. They're going to get there. But what they really don't have is a visual cortex. If you can think in 3D, you're ahead of the AIs. So basically, sort of how things fit together, sort of mechanically, think about electronics is probably unique to me. but do things where, some kind of visualization that the robot is, it's an AI don't have yet. I mean, I'm trying to build it. So if you look at computing in general, this that you get now is mostly 2D, 1.5/2D compute surfaces. So something like a GPU is a 1.5 at best compute surface. It's a pipeline. Cerberus do 2D. They're doing wafer scale giant 2D things. Nobody has physically 3D compute. At this point, I can see that the hardware is there to do it. We're looking at optical communication between things. Can do something where you just do layers of 2D computers, stick them together. The problem is if you do that in a box with the NVIDIA stuff, then it melts. So this is where Electronics, I think it's going to happen is that you will get a lot of assistance from the AI on validating your ideas. So the AIs will tell you is good or bad or doable. What you need to understand is basic physics principles and mechanical engineering principles, not necessarily the detail of the math of how to do things, but the principles. So, I did physics before I did electronics to some extent. And that's a useful basis for, is something actually possible? And there's things like photonics that are coming up now in open compute, projects, and photonics is kind of physics based. So I'm finding that the physics still, 40 years since I was at college. So some of the things I learned at college are still good because they're fundamental. So the laws of physics don't change. So those are good things to learn because they're the same forever. The quantum computing thing, that was an interesting one. I'm not sure how people are going to use that at all, but base where there's not a lot of people. I generally sort of say try go do something where it's like robots and AI can't do yet if you're looking for a job, or just do what you like. It's like, a lot of people now who move into electronics because you can actually build things very cheaply, like the Raspberry Pis and the add-ons and things just plugged together, and find that most things don't blow up these days like they used to. I had something that blew up the other day, but you can plug things together and they take the abuse much more than they did when I was learning electronics. The reasons I didn't do electronics at home was that I tried it one time, and I could tell I was getting it wrong because I was getting a lot of interference in the radio I was listening to. Things you just like, they bop and you get expense blow up. But not
Always,
doing it in simulation.
yes, a good idea to be well grounded in
Yeah.
always, right? Yeah.
Physics, math, I don't think you really need to understand them that well, but you need to understand what the capabilities are. AIs will do some stuff for you now. You kind of know what's possible, but not the details doing it. It's like Einstein, but Einstein's theories are relatively well sounded, and sometimes they apply.
Yes.
It's like I don't have to work it out for myself. The AIs and will do the math for me and tell me whether some things are doable or not. So I kind of fit from that level and say learn the things that the AIs are not good at, and so far that's like anything to do with street visualization probably.
So how can somebody, those aspiring young people, get involved with Present Energy or contribute to the fields?
We actually had some students from San Jose State working for us on robot stuff. So basically the idea was like, do a prototype robot for us, and like I get a piece of video that I can show to somebody and say, hey, this is the robot we're building. So I would say one of the things is when I was at college, they didn't really teach me as an engineer how to make money. So I think that the thing with students, if you look for people who are wanting sort of commercial sort of proof of concept type stuff, you can find a project where somebody will give you some money to go build something, and I usually try and cut the stuff down to sort of project size chunks if I can, and say, hey, do this one piece. Like sort of simulators, you can go to somebody who's in a computer science course and say, hey, add this piece. Add a language, that's your project. And trying to sort of do things at a time in the direction you want to go.
Kevin, this has been an incredibly insightful and valuable conversation. Thank you for sharing your expertise and the work of Present Energy with us.
Oh, thanks very much for inviting me. It was fun. We can do it again.
Sure. And to our viewers, thank you for joining us on Clean Titans. Please subscribe and follow us for more insights into the world of clean energy and technological innovation. Until next time, stay energized and keep innovating.